Okay, we now know about L'Hopital's rule and how it's used to calculate limits. Let me just remind you, if you have the limit as x tends to a of f of x divided by g of x, so one function divided by another, where f of a and g of a are both 0, so in other words, you can't just calculate this value by putting in x equals a, then L'Hopital's rule says that's the same as the limit as x tends to a of f dash of x over g dash of x. In other words, you can just differentiate f, differentiate g, divide one by the other, and that will give you the same limit. Right, and this also works if f of x and g of x aren't 0, but instead both go to infinity as x tends to a. Alright, so if in this first case, if you have f and g both being 0 at x equals a, then we call it a limit of the form 0 divided by 0. And in this case, we would say it's a limit of the form infinity divided by infinity. Right, so what about this one? What about the limit as x tends to 0 from above of x to the power x? So here's an example. Now this example doesn't fit into either of these cases, but it's still problematic. It's certainly not one thing divided by another thing where both of those are 0 at the point we're interested in. It's also not infinity divided by infinity. But this is something just as problematic. If you put x equals 0 into here, you get 0 to the power 0. Which of course you can't evaluate. Your calculator won't do that for you. So there's a problem with this limit. X to the power x is undefined at 0. What value does it get close to as we get x smaller and smaller? Right, now there's a technique here. Luckily, if we do a bit of rearranging, we can just use L'Hopital's rule. Let me show you how. So to get going, let's write L as this limit. So L is the limit as x tends to 0 from above of x to the power x. Now, the rough idea here is that we can take logs and transform everything into a form that L'Hopital's rule applies in. Okay, so precisely what do we do? Well, we just look at this function where we have log of x to the x instead of just x to the x. Now, if we think about the limit as x tends to 0 from above of that function, so this is where we take the logs of all the values here, then of course the limit will be log of this number L. Right, so log of L is the limit of log of x to the x, and of course the rules of logarithms allow us to write that as x log x. Now this one is familiar to you from the previous video where you were shown that this has limit 0. If you remember, you write this as log x divided by 1 over x, and then L'Hopital's rule applies. Okay, so we found that log L is 0, and therefore L, well, that's just going to be e to the 0, which is 1. So we found our limit. The limit as x tends to 0 of x to the power x is just 1. Now, in fact, you could draw a graph to see what's going on here. If you calculate some values, for example, when x is 2, the function is 2 to the power 2, which is 4. So that's up here somewhere. When x is 1, you get 1 to the power 1, which is 1, so that's down there. When x is a half, you get a half to the power a half. That's the square root of a half, which is 1 over root 2. That's about 0.7, so it's somewhere there. But in fact, what happens if you keep calculating values, it's dipped below 1 here, but you find it starts going back up again, and in fact the graph looks like this. So technically, it's undefined at x equals 0, but if you get closer and closer to 0 with your values of x, you'll get closer and closer to 1 with the y values here. And in fact, you can check, if you like, using calculus, that the minimum point occurs at 1 over e. Right, so this same technique can be used in other cases. So you can also show things like if you have the limit as x tends to infinity of x to the 1 over x. Again, you can do this trick of taking logs and then calculating that limit. And in fact, what you get here is again 1. Now this is a limit. Of course, there's a problem here. As x tends to infinity, x gets really big, so this bit gets really big, but this bit gets really small. And really what you're trying to calculate here is infinity to the power 0, which of course you can't do. That's why we need some kind of technique. But the same approach works there. And here's another example. Limit as x tends to infinity of 1 minus 1 over x all to the power x. So what's the problem here? Well, as x tends to infinity, this bit gets closer and closer to 1, but this bit gets infinitely big. So this is a limit of the form 1 to the power infinity, if you like. Again, you can't just put the value of x in and see what happens because it's ambiguous. But what you get here by the same method is 1 over e. So you could try those if you wanted to. Right. Now here's another example. What about this one? A limit as x tends to 1 from above of x over x minus 1 minus 1 over log of x. Right. So what's the problem this time? Well, if you put in x equals 1, then you get division by 0 here. So this bit gets infinitely big. This bit, when x is 1, remember log of 1 is 0, so again you get division by 0, and this bit's infinitely big. So this is something of the form infinity minus infinity. Now it's tempting to say that if you take one thing away from another like this, you'll get 0, but that doesn't always work with infinity. It's a bit more subtle than that. So how do we calculate this limit? Well, we can't use any of the techniques we've got already straight away. It's not one of these forms, it's not one of the standard forms for L'Hopital's rule. What do we do? Well, luckily here, a bit of simplification does the job, because if you want the limit as x tends to 1 from above of x over x minus 1 minus 1 over log x, then you can just write that all as one fraction, and we'll see how that helps. It's the limit as x tends to 1 from above of x log x minus x minus 1, all divided by x minus 1 times log x. Right, why is this better? Well, if we put in x equals 1 here, which is what we're trying to find the limit for, you get 0 from this first term because log 1 is 0, 0 from this term because x minus 1 is 0, so the top is 0. As for the bottom, well, you get 1 minus 1 here, so that's 0 as well. So we get 0 over 0, and that means L'Hopital's rule will apply. We can just use L'Hopital's rule here. So this is L'Hopital for 0 over 0. And if you do the working, what you end up with is a half. So it wasn't 0. Infinity minus infinity doesn't always give you 0. Okay, so those are some techniques that you can use for solving more difficult limits. Roughly speaking, you just need to play around with your expression, maybe take logs, maybe simplify, and see what pops up.